the cloud. Why is that so loud? Okay, whoever liked my YouTube video, thank you. I thought it was hilarious. I saw the number, I can see the number of views, and there's like 39 views. I was like, oh, people are studying. That'll happen. 39 out of 110. So it was okay. The ratio isn't 2 there. It's 3 out of 3/10. Where in the world is the black marker? Dang it. Okay, fine. So now chapter 5. So what do we talk about in chapter 4? Probability. What's going to talk about chapter 5? Probability distribution. So what does that mean? So many decisions can be made by assigning probabilities to all possible outcomes pertaining to a certain situation and then evaluating the results. For example, I can assign probabilities to the number of students who get an A, B, C, D, and F in the course. This is called a probability distribution, and the definition is as follows. So I'm just going to put the first one. So a table, graph, or list that, how would I say this? I can't remember how I put it. That lists all the possible values. That's not how you spell list. All the possible values a variable can take on. And their corresponding probabilities. This is getting really dim really quick. I think I have some. I don't know. Let me see. I have vis-a-vis markers, but that's very thin. Let's see. That's going to have to work. I don't know where it went. It's not behind here. What the heck? I guess so. I guess someone threw it away. Okay. So, yeah, you can't read that. So, I read it. So, there will be 2 types we'll talk about. So, before moving on, let's review the difference between discrete and continuous. So, I can't remember if I put this on. I don't think I put the definitions on your exam. So, discrete variables contain values that are countable. So, think of it this way. Discrete, countable. Okay, they can read that online somewhat. Continuous. Infinite. So it says continuous variables contain values that can be any value in an interval. Any value just means an infinite number of values. So in this chapter, we specifically look at discrete probability distributions. So where the number of random variables that we're going to look at can be counted, and then each of those has an associated probability with it. So section 5.1 is all about probability distributions. So a variable is a characteristic or attribute that can assume different values. That's just the definition we talked about in chapter 1. Since the variables in this chapter are associated with probabilities, we're going to call these random variables. So why is it random? because probability is determined by chance. So chance is that last blank there. So you don't need to know that part. So you may need to know this next definition. I haven't decided yet. So a discrete probability distribution consists of the values a variable can take on and the corresponding probabilities. So if you have a continuous random variable, can you list out all the possible values and their associated probabilities? What do you think? If it can take on an infinite number of values, can you write down an infinite number of values? No. So this chapter is a little bit easier then. So let's look at this first example. So we actually did this thing in chapter 4. So what does it say? If a fair die is rolled, what is the probability distribution? Or it says here is it. I don't know if I already gave you it or not. So let's just say this is the number you roll. And this is its corresponding probability. You can either roll 1, 2, 3, 4, 5, or a 6. And all of these are equally likely to happen. So they each have probability of 1/6. So what do you notice about all of these probabilities? So when you add up all of the probabilities, what does it give you? 1. So then the first rule, I guess this is actually the second one is what I say. So the second rule is the sum of all the probabilities gives you 1. So these are the requirements that make it a valid probability distribution. What is the first one? We talked about this the very beginning of chapter 4. What values can a probability take on? Between 0 and 1, including 0 and 1. So the first one is the probability of each individual outcome in the sample spaces between 0 and 1. If these two conditions are satisfied for such a distribution, we call it a probability distribution. So what we're going to talk about in this chapter is what is the expected number that I can attain at a die roll? What am I expected to get on any one roll or any 2 rolls? What's up? Yeah, 1 through 6, but I'm saying like what's the average number I would get? So we'll talk about how to find that. So now look at the next example that it says, is the following a probability distribution, why or why not? So someone already said the answer. So what is the thing that I wrote down? 1, 2, 3, 4, and 5. Oh my Lord, does this not come off? Oh, lovely. Who cares? We'll let the next teacher do it. Gosh dang it. We'll do this. Today is a mess. Lovely. This is great. Yeah, we're going to go back to the document cam. Let's go look like a hot mouse. I do, but that makes it not as crud. Why is it like this? Wait, I have an idea. Let's do this. Turn it on and then turn it off. Nope, the other way around, what I just said. No, on. It's not very good at this moment from what it looks like. Okay, now is it? No, still not shown yet. Golly. There it goes. Okay, it still sucks. Hey, there we go. Oh, no, never mind. Let's try it. What does auto tune do? I have no idea why it's doing this. Just do this. Zoom in. Okay, can you read that? Oh my Lord. Okay, we're gonna do this. Yeah, it's already on. I don't know why. Let's see. This is a great day. I guess so. Hello. What the? It worked for a second. Yeah, I tried. I've been zooming in and out and it still doesn't work. I don't want to call IT because I've never called them and I don't want to look dumb. So what are we going to do? I'm just going to show the completed one and I'll walk through it on Canvas. Golly, today's a mess. No, it is not. I didn't get enough sleep. I'm sleepy. I got a 19.5 out of 20 on my homework. Not fair. Here it is. There we go. We'll look at this. Share. Here we go. Oh, yeah, it's just your screen. And turn this camera off. How to turn the camera off? There it goes. Ta-da. Okay, now we're showing the screen. Oh, well, they've been recording this whole time. It's going to be a mess. Maybe I should publish this one to YouTube instead of being unlisted. Oh my God. Okay. Therefore, is the following a valid probability distribution? Why or why not? Yep, whatever she said. So first rule is all the probabilities between 0 and 1. So yes, they're all positive. That's all you're gonna know. So part 2, does the sum of all of the probabilities equal 1? So add up those. 0.2 plus 0.6 is 0.8, plus 0.1 is 0.9, plus 0.3 is 1.2, plus 0.05 is 1.25. So does 1.25 equal 1? No. So therefore, it's not a valid probability distribution. I can't remember if there's another one in here that I talked about or not. So let's look at this one. 3 fair coins are tossed consecutively. Create a probability distribution for the number of heads. So here is all the outcomes in the sample space. How would you find all of those? Yeah, 3. So just do heads, tails 3 times, and you'll get those outcomes there. Head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. So with these outcomes in the sample space, we're going to let the random variable x be the number of heads. So how many heads could we get then? So you can get up to 3 and you can get 0 heads. How would you get 0 heads? Tail, tail, tail. That's just what I was asking. So I'm just saying, how many times can you get a head if you roll it 3 times? That's all these x values can take on 0, 1, 2, and 3. So then it says create the probability distribution for X. So then X is going to be the number of heads, and these PXs will be the corresponding probabilities for each of those. So what do I need to do? I need to first look at 0. How many ways can I get 0 heads out of this sample space? The only option there is tail, tail, tail. And there's only one of those out of how many total? 8. So the probability of getting 0 heads is 1 out of 8. Then using that same idea, I can look at the number of heads, just 1. So if I do that, I'm going to go in here and look at these and where just we have 1H. So 1H would be right here at head, tail, tail, here at tail, head, tail, and here at tail, tail, head. So that's 3 ways out of 8 possible events or 8 possible outcomes. So the probability is 3/8. Then I go to 2, where I have 2 heads, so 2 H's in there. So that would be head, head, tail, head, tail, head, and tail, head, head. That is 3 ways again. So 3 out of 8 again. And then the last thing, 3 heads. What's the only way that can happen? Head, head, head. So there's only one of those out of 8 possible, so 1/8. So if I add up all those probabilities, what should I get? 1, and that is what I get indeed. 3/8 plus 3/8 is 6/8 plus 2/8 is 8/8 or 1. So this is a rough graph of the probability distribution. So if you just have this x-axis here is the random variable and the values it can assume, and the y-axis is just the height is represented by the probabilities. So if you draw a curve over this, what is the shape of the curve? Bell-shaped or symmetric? So we will actually talk about the bell-shaped and symmetric distribution. Next chapter is called the normal distribution. And it will eat some of your lunch if you don't pay attention, because we will use it the rest of the semester. After that, at least. So when given a survey, students were asked how many hours they studied last night. Let the random variable x be the number of hours studied. Given the following frequency distribution, create the probability distribution. So, how many hours did y'all study last night? I didn't study at all. So, I have a test on Thursday, but we'll see how it goes. So, then using these values here and the number of students associated, create the probability distribution. I will walk around and see if you do it right. That way y'all have to do it instead of me. So in this case, how would you represent the probabilities? It actually fills in the next blank. So remember that probability is represented by what? Relative frequency. So that's what goes there next. So then using the relative frequency of each of those, you can create the probability distribution. So do it just like I had up here. The random variable is in the top, and the corresponding probabilities to those random variables is in the denominator. Or in the bottom, not the denominator. Everyone here got their exam back, right? Checking again, cool. Okay. Gosh dang it, it does it on this computer too. Can I zoom in at the very top? That way you can't see anyone's. How do I get all the way over here? There we are. No, grade. Oh, there it is. Post grades. Graded. Post. Just this one. Thankfully. Okay, now I can zoom back out. So you just got an email that says submissions posted, exam 1. So you can see your grade and how it affected your overall grade so far. So for the number of hours studied of 0, what is its corresponding probability? 6 out of 27, just the relative frequency. The next one, 1 hour, what is it? Next hour, 2. Next hour, 3. Next hour, 4. Next hour, 5. 0. It was a trick. So that's what it should look like. So the third example, recall that a probability distribution can be represented by a formula. So let's say a random variable X can take on values that are 2, 3, and 6. If we denote its probability function by 1 over the value the random variable takes on, then create the probability distribution and verify that it is actually a proper probability distribution. So how would you do that? So what would be the probability that the random variable takes on value 2? Yeah, 1 over 2, just plug it in the formula. So the probability that X is 2 is 1 over 2, or 1/2. What about the next one? The probability that X is 3, 1/3. And the probability that X is 6, 1/6. What is 1/2 plus 1/3 plus 1/6? 6 over 6. So if you actually do the math, so 1/2 over 6 is 3/6. 1/3 in terms of 6 is 2/6. 3 plus 2 plus 1 is 6. So yes, it is indeed a probability distribution. So the next thing, well, let's see if there's anything easy on your homework you can start on before I get to that part. Oh, by the way, it lets me know how many of y'all have procrastinated, and I always love seeing it. It's about the same as the number of students last semester, actually, which I was shocked. 4.1, that's what we're in right now. Okay, so this should be pretty easy. Okay, yeah, I think it's easy. 3. So the probability that it will rain tomorrow is 0.2. What is the probability it won't rain? Yeah, it's chapter 4 homework. Oh, shoot, why am I doing 4? Gosh dang it. Here we are. I was like, that's too easy. Here we are, this thing. Okay. Oh my Lord, I hate these ones. State whether the variable is discrete or continuous. The time spent watching a movie. I think it's continuous because it's time. Let's see, time. Yep, time, continuous. Okay. It's very, very tricky because if you say time like the nearest minute, technically it's still continuous because you can take on an infinite number of minutes. Yeah, technically. Yes.
Interesting. Okay.
Yeah, so they consider time to be infinite because there's no end to time, I guess. Yes. Okay. Yeah, that'd be fine. So the square footage of a house, discrete. Let's see it. Let's make sure it says discrete. Oh, it says continuous. Nope. Okay. Yes, I can. So square feet. You can have like, oh my Lord, and it changes it again. So the height of a building. Okay, height is continuous. We already talked about this. So height is continuous. Therefore, this one's continuous. I'm not going to worry about the answer because I know that's right. What was the other one that it just said? Okay, square footage of a building. So say, for instance, it can take on 0 square feet, so you don't have a house, or it can take on upwards of Jeff Bezos' house, whatever square feet that is. There's an infinite number of decimals in between those values. Does that make sense? So it depends how many decimals you round it to. But theoretically, there are an infinite number of decimals. Okay. Yes, that. Some of your homework is not fun. Okay, this one is kind of easy. So determine whether the distribution represents a probability distribution. So all you have to do is check the rules. So is this one a probability distribution or not? No. Why? There's a negative probability. So it says the distribution is not. Oh, won't let me choose it. State why. The probabilities cannot be negative. The sum of the probabilities of the events. Let's see, is it equal to 1? No, it's not equal to 1 either. So both rules are violated. So holy cow. Oh my Lord. Okay, at least most of this is easy. Okay. Okay, here's the one by our formula. So write the distribution for the formula and determine whether it is a probability distribution. So it says the probability of x plus 1.3. So it's the probability that x equals 0.05. 0.35. What about 0.16? Yes. What about 0.21? 0.51, yes. Do those sum to 1? I don't know. 0.3, I think they go over it, it looks like. 0.35 plus 0.46 is what? 0.7 something. Yeah, it definitely goes over. So no, it's not a probability distribution. Ta-da. Okay, I think that was the last one I did. Yep. So all your homework is basically so the first section, it's checking whether it's a probability distribution or not and saying why. So all you have to do is check those 2 rules. Do all the probabilities are between 0 and 1, and does their sum equal 1? If it does, it is. If they don't, it's not. And tell it why. Leave. Okay, where was I at? Here. So section 5.2, the mean, the variance, the standard deviation, and the expectation. So this will get all sorts of confusing real quick. So in chapter 3, we learned how to calculate the mean, variance, and standard deviation for a data set. We can do the same with the probability distributions. However, the methods change. So what in the world does that mean? So if I have a discrete probability distribution, so I have each value that the random variable can take on and its associated probability, then the way I will find the mean of that random variable is to take each individual number it can take on, multiply it by its probability, and then add them up. So why? Probability was represented by what? Relative frequency, right? So then I have the number of times that value can occur divided by the total number of times. And then I have the sum of the total number of times. All it's basically doing is saying, say I have X takes on values 1, 2, and 3. Gosh dang it, why can't I write? This just makes it no fun. What it's saying is, say I have a, gosh dang it, screw it, we're gonna do it anyway. Yeah, I'll go get one after class. So say I have 1, 2, and 3. So this is 1. No, yeah, that'll work too, I guess. Yeah, say it's 1/2, 1/3, and 1/6, I guess. Ta-da. So that means that 1 occurs half the time. So let's say I have 6 values. So if I have the probability of 1 occurring is going to be half the number of times, that would be occurs 3 times, right? If I have 2 occurs 1/3 of the time, that's 2 times. And if I have that 3 occurs 1/6 of the time, that's just 1. Okay. Take the mean of those numbers. And what do you get? So 1 plus 1 plus 1 is what? 3 plus 4 is what? Plus 3, 10 divided by 6. Okay. Use the formula right here. X times the probability of X, and then add all those up. 1 times 1/2 is what? 1/2. 2 times 1/3 is what? 2/3. 3 times 1/6 is what? 3/6 or 1/2. Did I mess that up? Okay, 1/2, good. 2/3, good. 1/2, 1/2. Okay, that is right. So 1/2 plus 1/2 is what? 1, 6/6. That's how I'm gonna write it. 2/3 in terms of sixth, how many is it? Yeah, 4/6. Just multiply the numerator and the denominator by 2. 6/6 plus 4/6 is what? 10/6. It gives you the same thing. So think of it this way. I have a total number of times that something can happen. And this probability is representing the relative frequency of it, right? So if I know the total number of times something happens, I can find the number of times this will happen, just like we did here. The number of ones we have is 1/2 out of 6 times is 3. And I can do the same thing for each of those. If I take the average of this, it's the same thing as doing this. All it is taking the relative frequency instead of the actual frequency. Does that kind of make sense? Okay, just use that formula if it doesn't make sense. So it's kind of hard to explain why it is. Sometimes you just have to use an example and show it works. So the variance, this one is so much fun. So the variance of a random variable with a discrete probability distribution is found by, oh my Lord, I hate this. The expected value of X squared minus the expected value of X, that quantity squared. Is there a difference between this and this? There is indeed. Or, yeah. So in this case, so we have the expected value of X. Oh my Lord, we're just gonna have a great time up here. So the expected value of X is equal to the sum of the X's times their corresponding probabilities. So you can actually write this in terms of the expected value of X to some power, say X to the R. The expected value of X to the R, so using the same idea. So R in our case was what? If we're just looking at the expected value of X. R is equal to 1, right? So then it was x to the 1 times the probability of each individual x and add them up. So using the same idea here, what is the expected value of x squared? So you take each individual x value you get. Dang it. Take each individual x value, square it, multiply it by its probability, and then add them up. So what is the difference between that and the first one? So here we just have xi. So in the second one, the expected value of x squared, these xi's are squared. Their probabilities are not squared. If you square those probabilities and add them up, what will you get? Anyone got a guess? You'll get something less than 1. Can anyone tell me why? It's a more theoretical thing. It's kind of why. If you take any number between 0 and 1 and square it, what happens to that number? It gets smaller. So if I'm adding a bunch of numbers that are getting smaller as I raise it to a higher power, that sum is going to decrease, right? So that's why. So this probability will still remain the same, but each time I take these xi values that the random variable can take on, I need to raise it to the second power. And then I can find the expected value of x squared. So what is this part right here? So it's just the first part squared. That's all it is. The expected value of x is this mean. I'm taking that mean and I'm squaring it. That's all it's doing. So usually I put this on the exam. I don't know if I will or not. So I will have a problem where I say, find the mean, find the variance and standard deviation. So all you'd have to do is use this distribution here and use these rules. So let's look at, I guess I have to show it, that way they can see it. Let me see. Oh, yeah. So what I'm going to do is look at the example on the board. So this one right here, we're going to find the variance of it. It's going to be a hot mess because everything's messed up, but we'll be okay. So the expected value of x we already found was this 10/6. This is the expected value of x. Only thing you need to find is the expected value of x squared. So the expected value of x squared. So I take each individual x value that it can take on, I square it, and then I multiply it by its probability. What is 1 squared? 1 times 1/2 is 1/2. 2 squared is what? 4 times 1/3 is what? 4/3. 3 squared is what? 9. 9 times 1/6 is 9/6. I don't know what that sum equals. Take the sum of this, then subtract off 10.86 squared. So square that number, don't square the difference, but square this number and take that minus that one. And that'll give you the variance. So then once you have the variance, what can you do to it to find the standard deviation? Take the square root. So that is the formulas. So if you want to do the next example, find the mean, the variance, and the standard deviation. I will post it to Canvas and you can do it for bonus. Is that okay?
Yeah.
Okay. If you all have any questions about how I graded your exam, let me know. Otherwise, have a good day.